The purpose of this video is to help you learn how to approach solving an initial rate problem. In this problem, we're asked to find the rate law, including the value in units for k. Notice that in each trial, we're given a value for concentration of A, concentration of B, concentration of C, and an initial value for the rate. In order to determine the impact each reactant has on the rate of the reaction, we'll compare among trials to see if we can determine how the rate is affected by each. I'm going to start by comparing trials 1 and 2. You'll notice as you examine trials 1 and 2 that only the concentration of B has changed. In fact, B has a little bit more than doubled, and you'll notice that there is no impact on the rate. This tells me that B, since it has no impact on the rate, the reaction is zero order with respect to B. Next, I'll compare trial 1 to trial 3. In trial 3 and trial 1, concentration of B and concentration of C has remained the same, but the concentration of A has approximately tripled. The rate has changed, so we know that A does have an impact on the rate. In fact, if we examine the rates in trials 1 and 3 a little more carefully, we can see that the rate has gone up by approximately times 9. Since the concentration of A has tripled and the rate has gone up by a factor of 9, whatever we do to the concentration of A, we do the same thing squared to the rate of the reaction. Therefore, A is second order with respect, the reaction is second order with respect to A. Now all we need to do is try to determine how the concentration of C impacts the rate. When I glance back over this, I can find that between trials 4 and the other trials, the concentration of C has changed. Which row makes the most sense to examine? Well, B doesn't matter at all, but in trial 1 and trial 4, B has remained constant, C has changed, but A has also changed. However, between trials 1 and 4, the concentration of A has increased by a factor of 10. Based on our earlier work, what should happen to the rate due only to the concentration of A? Well, we'll notice whatever we do to A, we do that squared to the rate. So the rate should have gone up by a factor of 10 squared. Or, between trial 1 and trial 4, the rate should have gone up by a factor of 100, which would bring the rate to 12.16. What's the actual rate, though? The actual rate is 3.039, which is approximately 1/4, which is approximately 1/4 of the rate we would expect based on the impact of A. Well, examining the concentration of C from trial 1 to trial 4, we can see that C has been cut by a factor, cut to 1/4 of its original concentration. So we have cut C to 25% of its initial value, and we've also done the same to the rate, which means that C is, the reaction is first order with respect to C. Overall, that's going to give us the equation rate equals K times the concentration of A squared times the concentration of C to the first power. To find the value in units for the rate constant, we'll simply do some algebraic rearranging, and we'll find that the rate constant K is equal to the rate of the reaction divided by the concentration of A squared times the concentration of C, substituting in values from any of the rows, and quite frankly, you should be able to substitute values from one row and then check to be certain that you're correct by using the values from another. In this case, I'll choose the first row. The rate is 0.1216 molars per second, and we'll divide that by the concentration of A, which is 0.0152 molars, square that, times the concentration of C, which is 0.0572 molars. When I calculate an answer to this, I get that K is equal to 9200, and when we simplify the units, we will get 1 over molars squared seconds. And sure enough, if I use this value for K in any of the other rows, I'll get the same value for the rate constant, which tells me that I've done my work correctly.